thank the organizers and Mark in particular for inviting me to come, especially after the last one 4 years ago, which was so marvelous. I was thrilled to be asked to come back. So the last couple of days, it seems to me that maybe it's permitted now to omit the word small. Is that correct? I'm quite annoyed at the idea that we have to use the word category at all. But small is like adding insult to the injury. Okay, so let me this has sort of been done in various other contexts. So what do I mean by a left cancellative small category? That's I find it convenient, just write LCSC. And I can't stop now because I put this into a paper, so the S is stuck here. So what do we have? So we have it's a set. We have this distinguished subset of units. We have these range and source maps from lambda to the units. And then from that, we can define the composable pairs lambda upper 2. So the set of pairs alpha, beta, and lambda squared, so that source of alpha is range of beta. And then we have our multiplication from composable pairs to lambda, which is supposed to be associative. Let's see what else. I'm forgetting something. So we want, of course, on the units, range and source are just the identity. I don't actually know the formal axioms for a small category. I'm just sort of making up something that seems to describe what it is. I think I've seen them before, but I certainly didn't memorize. And the last one is that, of course, the elements of lambda 0 act as units, multiply as units. That's the basic idea. So it's this fundamental kind of algebraic structure. It's like a monoid, but with many units. So like it's a fundamental algebraic structure. So we always build other things from it. In particular, since I'm a C-star algebraist, there are various ways of building C-star algebras from things like this. And this process has gone along for quite a while now with lots of different situations. And so there's sort of a method of doing this. Oh, before I mention that, I should give some examples maybe here. So the first one is just a monoid. It's obviously a small category. And the second, which is for me the main motivating example, is the path category of a directed graph. So if E, that's usually given as vertices and edges with a directed graph, then we let E star is all finite paths, directed, of course. And then E0 is the space of units for E star, and that's an example of a small category. And that somehow is, of course, we all know how well worked over that has been from the C-star algebra point of view, and others. And so that's sort of one of the main motivating examples. Well, I'm going to be
sort of axiom, like describing the left cancellativeness in the list of.
So you're right. This is just small category. Yeah, you're absolutely right. Like the buzz phrase just pops out of the chalk, and I didn't think about it. So before I talk about the left cancellative property, let's go to the basic idea is that lambda acts on itself by left translation, right? So alpha, an element of lambda, acts on everything in lambda whose range is equal to the source of alpha. And if you multiply such a thing by alpha, you get something that's alpha times something, right? This just takes beta to alpha that's maybe the fundamental algebraic property of lambda is that it acts on itself by multiplication. So now the left cancellative property is exactly that this map is 1-to-1. Yeah. So these maps are 1-to-1 if and only if lambda is left cancellative. So in other words, that alpha beta equals alpha gamma, then beta equals gamma. So that's elementary exercise. But then we can actually do lots of things. And in particular, and I think this is really Xin Li's point of view. Well, before I say that, let me just point out that in this case, this left action embeds lambda into the family of partial bijections of the set lambda. Okay, so I'll continue with that thought in a moment. But first, to motivate where the C-star algebras come from. Once lambda acts nicely on itself, it acts on structures associated to lambda. So we can define what the left regular representation of lambda on the bounded operators on little L2 of lambda. Right, so this would be pi L of alpha on delta beta. That would be delta alpha beta if source of alpha equals range of beta, right? If they're composable and 0 otherwise. So pi alpha is a way of embedding lambda into the partial isometries of the Hilbert space. And now we're into this sort of C-star algebra setting. And so we can think about what kind of a map really is this, apart from being a homomorphism. So the partial isometries of a Hilbert space, well, let's see. So of course, partial bijections of a set, this is an inverse semigroup, but the partial isometries of Hilbert space is not. So this is more than just a homomorphism from lambda into this thing. So what are the key properties of pi alpha? What is the key property?
Pi L, Jack?
Pi L, yes. It's almost alpha, just turned.
Your handwriting's too good. That's the problem.
Oh. I'm really cringy, man. Nobody's ever told me that before. Let's see, so. Right, so here's where I wanted to begin mentioning names. So. Now we all have our own favorite origin story, but and I can't list everybody, but I would begin with Nika, and then Lotta Rayburn. Louis Exel, Kuntz, Lee, and of course, you look anywhere in this room, you'll probably be looking at someone whose name should be up here, along with many others. But to my mind, this is sort of where the ideas really came from. So here's the what I've distilled from this is the following key idea, is we try to extract a locally compact Hausdorff space from this axial lambda. So lambda, I think it's I only consider countable small categories. So it's really more elementary kind of object than C-star algebras or the other kinds of stuff we build out of it. So that's somehow coding some more detailed stuff. So how do you build the detailed stuff? The most important part is this space. So here's a place where you can do some analysis or build something. So how do you get a space out of this action? Okay, so because we have these one-to-one maps. So that alpha x is one. We also have the inverses. So let's note alpha inverse is also a one-to-one map. This goes from alpha lambda back to S of alpha lambda. Right, so now I'm move into unfamiliar territory for me. So I think this idea works. So we have this inverse semigroup I. Yeah, I just call it inverse semigroup. Generated by all these alpha. Right, so a typical element of this looks like alpha 1 inverse beta 1 alpha n inverse beta n for various elements of lambda. Oh, right. So this now I know the name for this is the left inverse hull. Well, I've been trying to learn a new language, and I'm going to use the words incorrectly, but I'm hoping to at least put some of the words on the board. Right. So if we let so this typical element, let's just call it phi. So the range of phi. So that's alpha 1 inverse beta 1 applied to lambda. So that's a called a constructible right ideal.
Is this by here just like a generic word in?
Yes, yes, a generic element of the excuse me, the inverse semigroup.
So if you always start with alpha,
So
an inverse, then how do you get alpha?
no, these could be units also, in which case it wouldn't really.
But if they always start with alpha 1 inverse.
Yeah, but if alpha 1 is a unit, then it might as well not be there.
Mhm.
So if you allow units, then you can get anything you want. Yeah, it's because that convenient way. No, I'm hoping Malcolm will talk about this tomorrow. Right, it doesn't matter in which order you write inverses and non-inverses, but the important ones really are coming in this form, where maybe you can't chop alpha off the beginning of something, but maybe if you put beta on, now some extension of that does admit alpha as an initial part, you can chop it off. So you get some interesting things when you do this combination.
So these alphas with sub indices are not related to the alpha and alpha inverse generating the inverse semigroup necessarily.
Okay, so these are arbitrary alpha and lambda. These are arbitrary alpha I and beta I and lambda.
Great.
Yeah, and n is arbitrary too. Right, so yeah. Yeah, I'm trying to write less because I take too much time. So now I'm gonna revert to my notation, which is not really standard, but I use this script E0 for the set of all such things. Write it this way. And this is it's easy to check. This is closed under intersection. And then I let curly script D be oh, so this is, I'm going to stop writing, but this is called the idempotent lattice of I. And now we look at all differences. So say E minus the union from 1 to N, say M, Fj, for E and the FJs belong to this curly D0. So that's a new collection of sets, and this is called the Boolean closure of D0. And then I let curly script A be the set of all finite disjoint unions of sets from this curly script D. And this, it turns out, is the this is an easy exercise, the ring of sets generated by D0. And now this is my choice in setting up the structure, is moving immediately to a ring of sets instead of working with more elementary kinds of things. But you can also prove that this is the smallest ring of sets containing all the principal right ideals. Let's see, so all things of the form alpha lambda. So principal right ideals and invariant under these maps. So now having that, I can tell you what this space is. Right, the key idea is to find this locally compact Hausdorff space, and now I can tell you what it is. But of course, there's various ways to do it, and my favorite way is a C-star algebraic way. So if we take an element of this ring A, then its characteristic function, think of it as a bounded function on lambda. So it's a little L infinity of lambda. So we can look at all such characteristic functions. They're closed under multiplication because A is closed under intersection. It's a ring. We take the span. Now it's a star subalgebra of little L infinity. So we can close it up in the infinity norm. I'm going to call that just E sub lambda. That's a commutative C-star algebra. So Gelfand tells us that it has a spectrum, and that's our space. So I call the space lambda star, which is by definition. So that's a very maybe a slick way of finding a locally compact Hausdorff space, and that's the one. Now you can identify this in many other ways. So this is also equal to the set of all ultra filters in this ring A. And it's also equal to the set of all characters on the ring A. The usual ways of describing this space. And it's not such a difficult thing to check that these are all the same. In fact, this is all basically Stone's theory, and I got it from Kelly's topology book.
Is it zero dimensional as well, or is that?
Oh, yes, yes, because these are projections. So so thinking of this as an element of a C-star algebra. Well, so it's a projection, it's a continuous function of compact support on its spectrum. So the support as an element of a continuous function here is a compact open subset. So we get lots of compact open subsets. Yeah.
So over here, these operations when you're defining D and A, are they just ordinary set operations in the power set of
Lambda.
lambda?
Yes, yes, everything's done with subsets of lambda.
And in A, that means that those subsets are disjoint.
Yes, this is disjoint union. So we insist. Well, and this is an elementary thing. If you have a collection of sets closed under intersection, then this is exactly how you build the ring of sets it generates, or one way of saying it. Yeah, so there's some little exercises in set theory that I discovered for myself when I was trying to figure out what was going on with this.
You get the same thing if you just take A inside D0 here? conform at the level of.
Let's see, so. There's a difference between D0 and D that's somehow very important. It's this idea of, I think of it in that sort of graphical terms, you're allowed to block finitely many ways into a vertex. But if there are infinitely many ways in, you can only block finitely many. So that's somehow this idea.
Well, the C-star algebras, you can see the union from the projections, I guess, as well, using this. I guess I was wondering if you take the closed linear span of chi A for A in 0. rather than-
Yeah,
inside.
yeah, I see your point. Yes, no, absolutely, that would be the same.
Yeah.
Yeah, so I didn't mention it here, you can assume that the FJs are contained in E if you want, because of intersections, but it's not. So, yeah, no, you're absolutely right, yeah. Okay, well, so you got the page, that's good. Right, so now we can let lambda act on this space. And now we have something where we really do know how to build C-star algebra, right? I should say this is actually acting by partial homeomorphisms. So this really gives us a pseudo group of partial homeomorphisms. And now it's fairly standard to build a groupoid. Though I should say that in the general case, there's more than one way to do this, and you get different things.
Yeah, so what exactly is the action? Are you going to tell us?
Oh, sorry, if you try to write down what it might be, there's only one thing you can do. So elements of lambda act on elements of lambda, hence they act on subsets of lambda. And every, let's see, so it just works its way up. So everything associated to lambda, you know, if you have a function on lambda, you can act on the inside. So yeah, no, I guess I'm sorry, I'm not going to write down. But I will in the special case I'm interested in.
When you say it's a like a partial, yeah,
PH is partial homeomorphism.
partial homeomorphism, but does it obey the usual, let's say, usual axioms of partial actions or?
Well, yeah. So that the composition of two makes sense and is in there. Yeah.
I mean,
In a way, this. Yeah, so all the sets you might get by intersecting the range of something with a domain of something that comes after it are handled by doing these kinds of things. So it really is
one other question.
Yeah.
Lambda is not a monoid, right? It's only a partial monoid.
Sorry, lambda.
It doesn't have an.
It's a small category, so it's not a monoid.
When you say pseudo group, normally a pseudo group involves a monoid rather than a category.
Oh, no, I think of a pseudo group as a collection of partial bijections of a set that's closed under composition, where you reduce domain in as necessary. So I don't think, yeah, so maybe I have a different sense of what a pseudo group is. There's like the notion that's written up in Arzumanian and Renault's paper on pseudo groups and groupoids.
Is this the same as like looking at the image of lambda in the inverse semigroup of partial bijections on or partial homeomorphisms on the space then?
Well, yes, right. So once you know how lambda acts, then you know how any such thing acts. So yeah, knowing how the individual elements of lambda act tell you how anything in I would act. Because once you know how alpha acts, you know how alpha inverse acts, and you can compose things, and so you can see how all these p's would act as well. Does that make sense? Perfect. Yeah.
Is this groupoid the same thing as the universal groupoid of this inverse?
I don't think so. In fact, I'm sure it's not in general. And this is one of the choices that I made in doing this process. And now I know if you look at Lee's papers on semigroup C-star algebras, he defines 5 or 6 different C-star algebras, one of which is the universal C-star algebra of the inverse semigroup. And they're related, but they aren't the same. There are maps between them in certain ways. And there are even elementary examples showing that you get different things.
Maybe a related question, sorry. So when you're saying characters of A, are you allowing the 0?
Oh, okay, so very technical question from my point of view.
Sorry.
No, I think not, because we really want the locally compact Hausdorff space, not a compact Hausdorff. I sort of think that the zero character is like the 1-point compactification of the space I'm talking about. So I would say no, it's no, in the same sense that the empty set's not an element of an open filter. I think, yeah. Okay, so once we have a group we get a C-star algebra. Okay, so I'm going to try to accelerate a bit. I guess I'm back to this thing. So I wanted to look at a special case. Well, so now the question that comes up is, once we have this E locally compact Hausdorff space, well, we don't really have it. That's sort of the general definition. But in any specific example, the problem is to actually find it. So it's a very general construction, and we would like to get something a little more explicit. And that can be done, right? Even in the general case, you can write down something more explicit, but it's complicated. But there's a special case which includes most examples that we know that are interesting. And that's the finitely aligned case. So let me give this definition. And here, this is from Rayburn, Sims, and Yeen. In fact, I was around and even vaguely aware at the birth of higher rank graphs. And I watched the progression of different ways of trying to deal with more complicated higher rank graphs. And I'm still astounded at this paper and how they managed to guess the right answer. It's really stunning if you think about what they were up against at the time. But now we have an understanding of this. So lambda is called finitely aligned, or I call it. And I think in the next talk, I'm going to find out that it's actually a much older notion, and it's really called Hausen. Is that right? Well, you don't know the definition yet, but that's pretty. So so there are various ways of putting it. So the way I find most convenient to use, if the intersection of any two principal ideals is a finite union of principal ideals. So for all, say, alpha and beta and lambda, there exists a finite set F in lambda, such that intersect these two principal right ideals is the union over elements of F of those principal right ideals. Another way of saying it is that every constructible right ideal is a finite union of principal right ideals. Another way of saying it is that, let's see, so if every element of the inverse semigroup, so let's write alpha 1 inverse, beta 1. So every map of this form can be written as sort of the union of a finite union of a coherent family of maps with the orders of the inverse reversed. So I'll call it a gamma J delta J inverse. So this is what in C-star algebras we sometimes call a kind of Wick ordering principle. That you can move all the inverse things from the left to the right and have everything in this special form. It's very easy to work with stuff. In fact, this is what Aiden told me when I asked him, why do we have to consider finitely aligned things? And he said, well, it's so we can do this. It's pretty obvious.
Does that last equation need lambdas on the sides of it?
Lambda.
Or otherwise, what do you mean by the union?
Oh, this is, no, these are maps, right?
Okay,
This is a function. each of these is a function, and this is supposed to be coherent. Coherent's the wrong word. There's a different word, compatible, coherent, compatible. So it means that anytime two of these have have overlapping domain and range, then they're doing the same thing there. So that function is just the set. So the union of the sets is still a function.
Chuck, if lambda is a monoid, it just implies that if two elements have an upper bound, then they have five domains.
It's a little bit more precise than that, right? Because there are examples where yeah, so any two elements that have an upper bound, they have a finite collection of minimal least upper bounds, but that's in the sense that every upper bound is above one of those. Right? There might be situations where there are upper bounds but no least one because there's sort of infinite descent. So but yeah, basically that's right. That's right. Even in this case, that. Let's see. And now, so I'm not going to talk about so much about how the groupoid looks and what the C-star algebra looks like, but okay, I'm just going to skip it. Sorry. So let me move on now. So here's a definition that comes from Nika's paper. So a subset X contained in lambda. Oh, so here I'm assuming that lambda is finitely aligned. So subset X of lambda is called directed if for all alpha and beta in X, there exists gamma in X intersected with the two principal right ideals, alpha lambda and beta lambda. So beyond, given any two elements in X, X contains something beyond both of them. That's the basic idea of direction. And hereditary, if say for all alpha and lambda, if alpha lambda meets X, then alpha belongs to X. So something beyond alpha is an X, then alpha is an X as well. So inherits things backwards down. And then the theorem is if lambda is finitely aligned, I guess I don't really need this definition here. I need it assumption here, this assumption. If lambda is finitely aligned, then this space lambda star is exactly the set of all directed hereditary sets. So that's a much more explicit description that you really can identify in specific examples. Now, let me just mention the topology in this context. So if we take a set from our ring script A, then I can define a subset of lambda star I'll call A hat. That's the set of all directed hereditary sets X with the property that A contains some tail of X. So there exists alpha in X such that A contains X intersected with the principal right ideal defined by alpha. And these will be basic compact open sets for topology. So you really have a very explicit recipe for understanding what you're trying to work with. Let's see, so. That's my generalities about left cancellative small categories. I'd like to talk about some examples. And let me mention that my motivation, and I should say, as many of you know, I'm a naive person, so my motivation is naive. So if we look at directed graphs. So as someone already mentioned, a directed graph is just a bunch of dots and arrows on a piece of paper. You can draw anything you like and you have a directed graph, and then you can do this stuff with it. So I would say in this setting, we have complete freedom. Okay, I'm not gonna try to write out exactly what I mean by that. You understand, just you can draw anything you want, then you're in business. Now, the next step up in directed graphs for higher rank graphs. So higher rank graph. This is a directed graph with identifications. So we have a directed graph E. We have an equivalence relation on E star. And lambda is the path category of the graph modulo this equivalence relation. But the rules are very strict. So strict that I found it's really hard to build them. And so I know some people are able to do this, but I find it, especially if you go higher than rank 2, it's very challenging. And you try to start building one and you're forced to add extra stuff in such a way that it becomes really hard to manage. So now we look at these left cancellative small categories. What is a left cancellative small category? Well, a small category is just a directed graph with identifications. And there are really no rules. Except of course, getting left cancellation. Right, so it's very much like defining a monoid by generators and relations. You can write down anything you want, but then you have to show that what you end up with actually is something instead of platform. So again, there's a deep problem here, but unlike monoids, if you're allowed to have lots of units and you don't put too much looping in to give you unwanted relations, it's often not so easy, not so hard to actually just write down some examples to play with and not worry too much about whether what you're getting makes sense. So this is my way of sort of breaking free of the restrictions of higher rank graphs in order to do so. So I spent a long time working with these things, and what I really want to show you is that something interesting does come out of it. Now these examples are joint with my former PhD student, Ian Mitchell. The first part of it in his thesis, and then together we sort of. So now we will cheat a little bit because we'll begin with a higher rank graph. Yes, sort of. So we have a sequence of vertices. So we have the following two graphs. So if you're not familiar with higher rank graphs, it won't matter too much. So it's a two-color graph. So I'm going to label, so these alpha 1, alpha 2, 3, and so on. Beta 1, beta 2, 3. And in this two graph, right, so we have to define the commuting squares. So we have a blue followed by red has to match a there's only one possible red bulb. There's only one way to make a two graph out of this. So we say that alpha I, beta I plus one should be beta I, alpha I plus one. Those are the identifications we have to make. And then this becomes a two graph. And it's a pretty elementary two graph. In fact, there's two graphs go. So actually, I said to Ian, okay, so, you know, I made you read this paper, what's a category of paths? What's the simplest non-trivial example we can come up with and try to see, you know, what C-star algebra is? And so we actually added an extra edge in this place. So we did this. So these are new edges. I would say this might be on gamma 1, gamma 2. And we can do this because we're not sticking to higher rank graphs, right? There's no relations between the gammas edges and the other ones. And we're not forced to try to make commuting squares. We just do this. We can do whatever we like, basically. And this is in fact an amalgamation of the two graph with the one graph. And so in fact, there's a theorem that says it makes sense as a left canceling small category, but it's not hard to just check that directly anyway. So we worked on this, and then Ian went home and he came back and said, you know, the golden ratio is hidden inside here. And so that was our first inkling that there was actually an interesting example. So he extended it to having several edges. So this might be gamma 1, 1 down to gamma 1, K1, and gamma 2, 1. Okay, only the same set of vertices, so it's very hard to draw them all starting at the same place. And we say K2 is the number of edges in the next place, and so on. And that's the family of left cancellative small categories that we studied. And it turns out that we have to allow the possibility that sometimes we don't add any edges. So it's actually nice to think of this as a very regular structure, this two graph, sprinkled with occasional impurities in the form of these edges. They might be very sparse. So what are we defining? We have this sequence K. Well, I guess I greater than or equal to 1. And to the infinity. And we insist that infinitely many of the KIs be non-zero. So here's the theorem. So given such a K, that T be a continued fraction. It's a non-simple infinite continued fraction. So 0, 1, 3, 1, 1, 8, 2, 1, and so on. And it turns out that's always an irrational number in the unit interval. And okay, so so I'm going to loosely write C-star algebra of this lambda. And I'm not telling you exactly which C-star algebra, because there's, you know, when you have a groupoid on a unit space, you can often restrict your attention to a certain closed invariant subset of the unit space to get quotient C-star algebras. And one of those is the Kunz-Krieger algebra, where you strict to what we call the boundary. That's in fact what I'm looking at here. It's really the Kunz-Krieger algebra, this thing. And it turns out it's isomorphic to what we call A sub T, which is the so-called F-Roshen AF algebra. So I don't really have time to give you a brief revision of the F-Roshen AF algebras, but AF algebras are certain C-star algebras. They're the closure of an inductive limit of finite dimensional C-star algebra. So they're locally finite dimensional and then closed up. So in some sense, elementarily presented, but they become very interesting, complicated C-star algebras. And these are famous ones associated to the continued fraction expansion of an irrational number. The usual one with all positive entries. So here we have this sort of non-standard continued fraction expansion that gives us a C-star algebra that is the same thing. And I should say that this relies on classification. So I like to call this Tequistis White Winter plus infinitely many other people.
Yeah, could I ask? So, okay, so you got a groupoid model then, let's say, yeah. And would this be the same as the sort of normal groupoid that you?
Yeah, thank you. That's exactly what I want to mention next. No, it's not. It's very different, which makes it all the more interesting, I think. Though it also means that there's something fundamentally hidden in it. So let me say something about that. Yes, this is not the same groupoid, and I can show you the reason. So let's see. So I'm going to have to write some things down that I haven't really introduced. But if we look at the following element of the inverse semigroup, so alpha 1 inverse beta 1. So we look at things where now I left off something here that's quite important. We actually have to compress to the projection at the initial vertex. Otherwise, we get something Morita equivalent. So we might say if look at things that begin with beta 1, but for which you can remove an alpha 1. So something that, for example, beta 1 alpha 2 can be written as alpha 1 beta 2, and then it begins with alpha 1, alpha 1 remove the alpha 1. So that's the kind of thing going on here. So this is a map in our inverse semigroup. And now, do I have lambda? I haven't told you what lambda star is. I meant to spend a while giving that in more detail, which I can't. So there is, okay, I think I have a minute. I can maybe say this. There was an element that I wanted to talk about here, that directed hereditary sets, you could think of them as, well, directed means it's sort of pointing off to some point at infinity, like an infinite path in a graph or a tree. But infinite paths are not really the right way to describe things in general, because there might be lots of paths that correspond to this. Well, you can't really describe an element of lambda star with an infinite path unless you understand how you're identifying things. It's a very dangerous thing to use until you really know exactly how you're doing it. So this is somehow the replacement for boundary paths, infinite paths, or finite paths in here. So in lambda star, we have what I call alpha infinity, beta infinity. And really it's so you can think of it as alpha, beta, alpha, beta, alpha, beta. As an infinite path, it might look like this. And that's the same as, say, beta squared alpha, beta squared alpha. Sort of any infinite path of alphas and betas that includes infinitely many of both. And what this means is we're looking at the directed hereditary set of all finite paths consisting only of alpha i's and beta i's. And with the commutation relations, it doesn't really matter how you present it. But if you just think of infinite paths, you might not think of these two as being the same, even though they are. Okay, so the idea is that this is now a point of our unit space. And if you let this element alpha 1 inverse beta 1, this map act on that point, what is it going to do? Well, it's going to add another beta 1 in front. Doesn't really change how many betas we have. Then remove an alpha. So it leaves this point alone.
Jack, I'm sorry, are those alpha 1 and beta 1? They're not the same as the alpha and beta in the next lines?
So this is a generic alpha and beta.
Okay, thank
Right?
you.
Because this is alpha 1, beta 2, alpha 3, beta 4. This is beta 1, beta 2, alpha 3, beta 4. We find alpha 6. So,
Okay.
it's an abbreviation that I just have to trot out without saying too much.
Okay.
Now, what does this mean? This means that in the groupoid, there's non-trivial isotrope. And an AF groupoid never has isotropy. So that's how we know that this is not the usual presentation of the AF algebra. Yeah, so ask me if I actually had read Blackadar's paper on the non-standard UHFs, which I don't think were given as groupoid models, but I wonder what the groupoid, if it would be some kind of thing, I have no idea. So this is the only example I know of presentation of an AF algebra by a groupoid that had. And I guess I had to stop there.